According to one, I am Dr. Prabhakar Swami of Mahatma Phule Mahavidyalaya. I heartily welcome all the respected participants. I am very much thankful to the chairperson of this session, the honorable principal of my college, Dr. R. Bodke sir. I request to sir, please chair session. I am very thankful to the guest for today's this national seminar series, session 17, honorable vice principal of my college, Dr. Vitalji Chavan sir. I request to Dr. Vijay Chavan sir to please chair the session. I am very much thankful to the person of this seminar, Dr. Pathan sir, for accepting our invitation and giving his valuable time to deliver his speech. I would like to first introduce to the today's honorable resource person, Pathan Amjad Khan Karim Khan. Sir is working as an assistant professor of chemistry at Adarsh Education Society's Arts, Commerce and Sir is having 12 years teaching experience in the field of chemistry. Sir is teaching physical chemistry since 12 years. His focusing area are atomic structure, electrochemistry, thermodynamics, experiments in physical chemistry using various instruments, which are conductor, protonmeter, and colorimeter. Sir is a good experience in research also. Sir has published 5 books in chemistry. Also, sir has Sir has edited 1 chapter in a book. Also, sir has published near about more than 10 research papers in reputed and Scopus indexed journals. Sir is having his own YouTube channel. On that YouTube channel, he has uploaded more than 35 videos on the UG and PG syllabus of chemistry prescribed by Swami Ramanujit Marathoda University, Nanded. Not taking much time between and the honorable resource person, I invite today's resource person to deliver his speech. Welcome, sir.
Thank you, sir. Thank you very much. So, respected principal, sir,
Welcome, sir. You are audible.
Swami, sir. Respected principal, sir, gave me a chance to deliver this lecture seminar on the topic of electrochemistry. Today, I will try to discuss one important theory of electrochemistry, that is Nernst theory of electrode potential. So, so kindly allow me to share content.
Yes, sir. Share. Yes, sir.
Okay. Is it visible, sir?
Okay, sir.
Green.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
So this series, national seminar series, is organized by Shri Chhatrapati Shivaji Shikshan Sanstha's Mahatma Phule Mahavidyalaya, Kingaon, which is affiliated to Swami Ramanand Tirth, Marathwada University, Nanded. Now, series started from 1st October to 25th of October 23 on focus on National Education Policy 2020 which is organized by IQAC in collaboration with NEP cell. So today's topic of my discussion is electrochemistry, and in that typically we'll discuss nuanced theory of electrode potential, which is useful for BSc as well as MSc students, and it's a kind of new knowledge for listeners. So let us discuss nuanced theory of electrode potential. So starting with that, so what is electrochemistry? So electrochemistry is a, we can say, branch of chemistry that deals with the study of interconversion of electricity and chemical reaction or chemical energy. Here, chemical energy is converted to electrical energy, and electrical energy is converted to chemical energy. Right. So when we use electrical energy to perform some kind of chemical reaction, then this is one branch of chemistry. And when we convert or use chemical energy to produce electrical energy, that will be another branch of chemistry. That will be another branch of electrochemistry, right? Now see. So here we are focusing on conversion of chemical energy to electrical energy, and there comes this nose theory in your nose theory. So which will focus on conversion of electrical energy to, sorry, which will focus on conversion of chemical energy to electrical energy. Okay, now to understand that, we must know what is electrode. Okay, so electrode is a metal rod or graphite rod. And what is electrolyte? So electrolyte is a chemical which have ions. It is strong or weak both. Electrolyte may be strong or weak electrolyte, like sodium chloride, potassium chloride, or copper sulfate, or zinc sulfate, and so on. There are many, a list of electrolytes. So this is the base of we can say modern cells or batteries. So whatever batteries we use in our smartphones, mobiles, laptops, watches, everywhere where we see rechargeable, mostly rechargeable batteries and dischargeable batteries, there comes this Nernst theory of electrode potential, right? So let us discuss first point of this theory, that is concept of electrode potential. Concept of electrode potential. What is electrode potential? Now see, according to this Nernst theory, all metals and hydrogen have tendency to lose electrons, to lose electrons. And when these metals are in contact with, say, water here, there is a tendency of metal to pass into solution as metal ion, right? There is a tendency of metal to go into the solution as metal ion. For example, see, so if you have a, say, one beaker, and in that beaker, if you place, say, metal electrode and fill that beaker with water. What happens? Okay, so say this is your metal, say zinc, this is water. There is a tendency of this zinc to pass into the solution as zinc ions, and it will lose 2 electrons, and these 2 electrons will remain on the metal surface, and this metal surface will have negative charge, and the solution is having zinc ions, right? So solution will carry some positive charge, and you can see this is negative charge on the metal rod, and to the surrounding of metal there are positive charge, and that develop electrical double layer, that develop electrical double layer, and thus there is development of potential. Here we can see the negative potential is developed and the reaction is oxidation. Okay, so this tendency of metal to pass into the solution leaving behind electrons is called as a solution pressure. That is called as a solution pressure, PS. Right, this is case number 1. Right, then there is another possibility that instead of using this water, if we use, say for example, metal is kept in contact with its own ions, like in this case, say you have a beaker, and in that beaker you have a metal rod made up from zinc, right? Then this solution is now containing zinc ions, for example zinc sulfate. So zinc sulfate, we know it will gives zinc plus sulfate ions. Now there is a tendency of this zinc to pass into the solution and leaving behind negative charge on the metal surface, and the solution will carry some additionally zinc ions. We know this tendency is called as a solution pressure. But if you have, say, copper as an electrode, and that copper electrode is kept in contact with its own ions, right, copper sulfate, then there is a chance that these copper ions from the solution will pass towards, will go towards metal electrode and get deposited on the metal surface. So how they deposit? Copper ions go to the metal, metal loses 2 electrons with the formation of copper atom, and copper atom get deposited on the metal surface. Thus this process is process of reduction. This process is process of reduction, and this electrode is continuously losing electrons and thus carrying what? Positive charge, and solution have excess or unbalanced sulfate ions. So we see here continuously deposition of, or there is a continuous availability of sulfate ions near the electrode. So this tendency of metal to get deposit on the metal surface, this tendency is called as osmotic pressure. Osmotic pressure. So one tendency we have seen is solution pressure, that is shown by zinc. Another tendency we have seen that is shown by copper, that is called as osmotic pressure, right? Now, on the basis of this, there are 3 possibilities. First, there is a chance that osmotic pressure is greater than solution pressure. or osmotic pressure then is less than solution pressure, or osmotic pressure is equals to solution pressure. So there are three chances. When osmotic pressure is greater than solution pressure. Remember, what is osmotic pressure? To pass into the, sorry, to get deposited on the metal surface, and metal will carry positive charge. What is solution pressure? To pass into the solution, and metal will carry negative charge. Solution will carry positive charge. So when there is a tendency of a metal to pass into the solution, then the to get deposited on the metal surface, we can see this situation. P0 is less than PS. When there is a tendency to get deposited on the metal surface, we have P0 is greater than PS. And when both are same, then P0 is equals to PS. So this happens here in case of copper. Copper accepts 2 electrons with the formation of copper. This happens in case of zinc. Zinc loses 2 electrons with the formation of zinc ions. And here there is no reaction. So this electrode is null. Okay. So when copper accepts 2 electrons with the formation of copper atom, the metal will carry positive charge. Metal will carry positive charge, or electrode will carry what? Positive charge. And the potential developed is electrode potential. Hence, this is the process is here reduction process. The process is process of reduction. So electrode potential is generally reduction potential. And the electrode have which charge? Positive. When there is a tendency of a metal to get to pass into the solution, then to get deposited on the metal surface, what happens? Zinc will pass into the solution, leaving behind electron. The process is oxidation process. Okay. And metal electrode will have excess electrons or negative charge on its surface, and thus electrode have negative charge and solution have positive charge. Thus, the process is oxidation, electrode carrying negative charge. So this potential is oxidation potential. What? Oxidation potential. And when the solution pressure and osmotic pressure, this one is solution pressure, osmotic pressure is same, there is no chance of development of any charge. Therefore, such electrode is called as a null electrode, right? So that is the base of this Nernst theory. Some electrode have positive charge, some electrode have negative charge. When we couple these two electrodes, positive with negative, we make one cell, and that is used in daily life, in mobiles, in smartphones, laptops, watches, and everywhere, remote controls in everywhere. So that was in brief introduction to Nernst theory of electrode potential. Now on the basis of this, we can proceed to the next point of the same, that is single electrode potential. Single electrode potential. So as we have seen, in case of zinc in contact with the zinc ions, and copper in contact with the copper ions, right? What happens here? When zinc in contact with the zinc ions, there is a tendency of zinc to pass into the solution, and zinc will carry negative charge, electrode will carry negative charge, and the solution will carry positive charge. And when we dip copper into in contact with the copper ions, like copper sulfate solution, then what happens? There is a tendency of copper ions to get deposited on the metal surface. Thus, metal electrode of copper will carry positive charge, and solution will have what? Negative charge. And thus, there is a development of electrical double layer. Metal, in case of zinc and contact with the zinc ions, will have negative charge, solution have positive charge. So electrical double layer is developed, and due to that there is development of a potential. So this potential is known as electrode potential or single electrode potential. Here this is negative. So when you see copper in contact with the copper ions, there is positive charge on the metal electrode and negative charge, unbalanced negative charge of sulfate ions in the solution. Again, there is development of electrical double layer. But here the potential is positive, solution carries negative charge. This is also electrode potential. This one is negative, this one is positive. Here we see oxidation reaction, here we see reduction reaction. Thus, this electrode potential is called as oxidation potential, and this electrode potential is called as a reduction potential. And thus, when we connect these two with each other, there is a flow of electron and there is making of a cell. Right. So when you see oxidation reaction, oxidation potential. When you see reduction reaction, we call it as a reduction potential. Okay. Then another term here is standard electrode potential. Standard electrode potential. Now always remember that when you see this word standard, that means it has specific or typical conditions. Right here, in case of standard conditions, the temperature is 25 degree centigrade, or you can say 298 Kelvin temperature. Now, when gas is involved, the pressure is kept at 1 atmospheric pressure. Now we know that here we already seen zinc in contact with the zinc ions and copper in contact with the copper ions. We have seen solutions. So concentration of solution is kept at 1 molar concentration. Right? Check once again. If the temperature is 25 to 98 Kelvin, pressure 1 atmospheric pressure when gas is involved, and the concentration of the solution is how much? 1 molar. Concentration is 1 molar. In that case, both reduction potential or oxidation potential, reduction or oxidation potential are called as standard potentials. So it is denoted as 0. So it is called as standard reduction potential, and this one is standard oxidation potential. Right? So what is oxidation potential? What is reduction potential? So for oxidation reaction, oxidation potential; for reduction reaction, reduction potential. If you are maintaining proper temperature of 298 Kelvin, pressure 1 atmospheric pressure for gases, and concentration of the solution as 1 molar, then that is called as a standard electrode potential, standard reduction potential, or standard oxidation potential. Right? Then now, which sign we should give to reduction potential and oxidation potential? And we have seen that in the case of reduction, the copper electrode carrying positive charge, and in case of oxidation, zinc electrode carries negative charge. Right? But that is not the base. The base of giving sign is here. So sign of electrode potential. Which sign will assign to electrode? There are only two signs. So one is positive, another is negative sign. So if we connect zinc electrode with hydrogen electrode, that is also called as standard hydrogen electrode, and if oxidation reaction takes place, what? Oxidation reaction takes place, then the potential given is negative. The sign of electrode potential is negative. Okay. And second case, so this happens in case of generally copper in contact with the copper ions. What happens? There is a tendency of copper ions to get deposited on the copper metal with the acceptance of electron. So when you connect this copper with standard hydrogen electrode, then if a reduction reaction takes place, which reduction reaction takes place, then the sign given is positive sign. So sign of electrode potential depend upon connection or connectivity with standard hydrogen electrode. So when it is any electrode, if it is connected with the standard hydrogen electrode, oxidation reaction takes place, negative. Reduction reaction takes place, positive sign. So in this way, we understand the signs or sign conventions of electrode potential when connected with the standard hydrogen electrode, oxidation, negative sign, and reduction, positive sign, right? Then next, now if we, as I said, if we connect these two electrodes, positive electrodes and negative electrodes, with each other, that develop one cell. So such a cell is called as a electrochemical cell or galvanic cell. So let us discuss the construction of electrochemical cell and galvanic cell. That means you will see the one electrode which is showing oxidation reaction, another electrode which is showing reduction reaction. So when you connect these two, that makes one cell. So what is the construction, how that cell works, or the what are the different reaction processes taking place in that cell can be discussed here. That is called as a electrochemical cell or galvanic cell or voltaic cell. So voltaic cell, what is that? So voltaic cell is consisted of two electrodes. One is zinc in contact with the zinc ions, another is copper in contact with the copper ions, right? Now here we already said that the chemical reaction is converted to electrical energy, or electrical energy, sorry, chemical energy is converted to electrical energy. How you are saying, or why I am saying that chemical reaction is taking place and that is converted to electrical energy? So show me the demonstration, how which chemical reaction is converting electrical energy. Here in BSc first year, we have one experiment in that we find out, we determine this heat of displacement. Heat of displacement. In that case, we take some plastic beaker, polythene beaker. In that polythene beaker, we have a solution of copper sulfate. Okay. We have solution of copper sulfate which has blue color. And on another page, we have some powder of zinc, generally 1 gram zinc. And while doing experiment, what we do is we so in the experiment, what we do is we initially find out the temperature of this and note down the reading. Say the temperature generally is environmental surrounding temperature. Say for example, it is how much? 25 degree centigrade. So when you measure this temperature as a T1, what happens? After that, we add this zinc powder into copper sulfate solution. So this experiment is presented in the BSc first year. We find out heat of displacement. That means here the reaction is copper sulfate react with the zinc with the formation of zinc sulfate and copper with the evolution of heat. The temperature rises. So when you mix this zinc, okay, so when you mix this zinc with copper sulfate solution, the reaction takes place. The reaction is this copper sulfate plus zinc gives zinc sulfate plus copper, and the temperature of the system rises around 4 degrees centigrade. Temperature is increased. The temperature reaches to sometimes 29 or 28 degree centigrade. We find out change in temperature, and using that change in temperature, we calculate heat of reaction. Overall, what I want to say is when you mix copper sulfate with zinc, heat is evolved. So that heat evolved or increase in the temperature is nothing but chemical energy. Chemical energy. In general, we see we have a say matchbox, and on the matchbox, if you strike, what happens? It burns, and the phosphorus in that react with the air, and heat is released, and we use that heat. Here again, this is chemical reaction and heat is released. Here, this is a chemical reaction, heat is released. The difference here is this is oxidation direct in air. This is the reaction takes place in the solution, liquid phase. So heat energy, what I want to say finally is heat energy is released. Now we want to convert this heat somehow to electrical energy. And this is done by using voltaic cell or galvanic cell. So how that happens, how they do this, how chemical energy is converted to electrical energy, what is the step, what are the processes. Now see the construction of voltaic cell. A voltaic cell is consist of beaker. So there are two beakers. One beaker having zinc, another beaker having copper. So this is zinc and this one is copper, and it is in contact with its own ions. So here copper is in contact with the copper sulfate, and zinc is in contact with the zinc sulfate. Then we connect these wires, external wires from zinc to copper, copper to zinc. And we know that what happens when you connect wires, what happens? Zinc will pass into the solution as zinc ions, leaving behind 2 electrons. Then these 2 electrons generated here will pass towards copper. And then these copper ions will accept 2 electrons with the formation of copper atom, and copper atom will be deposited. That process goes, and at one stage there is large amount of zinc ions present in the solution, and solution will resist further expulsion of zinc ions into the solution. And here in this case of copper in contact with the copper sulfate, most of the copper ions are deposited on the metal surface, and the solution having excess sulfate ions, excess negative charge due to sulfate ions, unbalanced sulfate ions, and these sulfate ions resist the passage of copper to the metal, and thus there is setting up of a equilibrium, and the process of oxidation here and product process of reduction here stops, and the flow of current stops. So for that, what we do is we connect salt bridge and start internal connection of these two solutions with each other. And then what happens? The excess sulfate ions from this side, excess sulfate from this side will pass into the solution through salt bridge and go towards zinc sulfate solution with the formation of zinc sulfate. And here the solution of copper sulfate is get diluted, copper get deposited on the copper sulfate as copper metal. Sulfate will pass into the solution, and these sulfate ions go through salt bridge and they go towards zinc sulfate solution. So zinc sulfate concentration increases, copper sulfate concentration continuously decreases, and there is continuous flow of electron takes place from zinc side to copper side, and this galvanic cell works continuously. When the total zinc is deposited, when total zinc is passed into the solution and most of the copper is deposited on the metal surface, the solution becomes extremely dilute. Then this reaction stops and the working of cell stops. Then what we do is we remove these solutions. The zinc sulfate solution is removed, copper sulfate solution is also removed, and these electrodes, zinc electrode and copper electrodes, are replaced with new electrodes. That means we recharge it once again. Where we charge it with fresh solution, fresh electrode, and the cell again starts working. Okay, so what happens? What are the different electrode reactions here? Zinc pass into the solution as zinc ions and 2 electrons. Then copper will accept 2 electrons with the formation of copper atom. This is oxidation. This one is reduction. So the potential developed here is oxidation potential, and the potential developed here is reduction potential. Here oxidation potential having negative charge, reduction potential having positive charge. So this reaction takes place. Overall reaction is the zinc indirectly react with the copper with the formation of zinc ions plus copper atom. Now remember, we have not mixed these solutions with each other. What we have done? We have not mixed these two solutions with each other. If you mix these two solutions with each other, what happens? When you mix these two directly with each other, heat is generated. Here, we are mixing these indirectly via external wires, and thus, finally, though this reaction will generate heat, but instead of heat here, the heat is converted to current, and the electrons will pass from zinc to copper continuously, and current flows from negative to positive. And thus, this heat is converted to electrical energy. In this way, by using this, we can say magical device, this very smart idea, this electrical energy is converted to, this chemical energy is converted to electrical energy, and thus galvanic cells work. Here we see there is one very important component we have used is our salt bridge. So salt bridge is nothing but a glass tube. This is inverted glass tube, and it is filled with neutral solution of either KCl or KNO3 or K2SO4. These neutral reactants are filled here, and to maintain its viscosity, it is mixed with some solidifying agent like gelatin. Okay, so why these chemicals are used? Because their transport numbers are same. The current flown by K plus and Cl minus is same. So here transport number of K and O2 is same. So these two chemicals generally are used in the salt bridge, or K2SO4 is also used in the salt bridge. So here we have a glass wool. It maintains the contact of the two solutions and allow transfer of ions, here sulfate ions. Then it maintains electrical contact indirectly. Okay, and thus If you don't use salt bridge, the voltaic cell or galvanic cell don't work. So therefore, it is necessary to use glass electrode, or sometimes we can use porous partition. Porous partition. What we do is, the porous partition have a ceramic material, and that ceramic, sorry, that ceramic material have very fine holes. So in this way, we have a pot. In that pot, we have another pot. In the center, we have zinc in contact with the zinc ions. Okay, and outside this container sometimes made of copper, and it is in contact with the copper ions. Okay, and this is porous wall. This wall is a porous in nature, and these two solutions don't mix directly, but there is a chance, there is a passage of sulfate ions. They can go from copper side to zinc side, and thus it also maintains electrical neutrality, allow passage of sulfate ions. The solutions are not directly mixed. If solutions are directly mixed, then what happens if you mix these two solutions? So when directly zinc is in contact with the copper, what happens? There is a direct reaction between copper and zinc, and copper is deposited, and zinc will pass into the solution. Instead of passing electric current from this zinc side to copper side via resistance, there is a direct mixing takes place. Instead of generating electrical current, heat is generated, and the temperature of the system will rise. That means we never get electrical energy. So we avoid direct mixing of these two solutions. Okay, so that is the role of this, either porous partition or salt bridge. Okay, then the next point. Now, next point is, we can lead towards the last, Nernst equation. Nernst equation. Now, what is Nernst equation? Before that, going towards Nernst equation, understand the background. Now, someone wants that, okay, the zinc, when it is in contact with zinc electrode, is in contact with the zinc ions. Okay, oxidation reaction takes place. Zinc pass into the solution with the permission of zinc and two electrons. Okay, and when copper is in contact with the copper, what happens? There is a tendency of copper to get deposited on the copper electrode with the reduction reaction. Right now, someone asked that, okay, this is oxidation and this one is reduction, accepted, but what is the potential? What is the exact potential of this oxidation potential or reduction potential? What is the value? Now, what to do? So, if you want to find out the potential of zinc, or if you're using copper, then if you want to find out the potential of copper, okay, where you will connect these cells? Yes, where will you connect these cells? Now, you tell me in general, is it possible to pass electric current by just connecting one wire? Say, for example, if you want to charge your phone, and one wire is connected to the electrical source and another wire is free. Now, you tell me whether this electric current will pass through the charger and whether it will charge your phone. No, one wire is open, but there is no chance of charging. That means you have to connect both positive pole as well as negative pole, then electric current will pass. So what I want to say is, there is no chance that you have just one electrode, either zinc or copper, in contact with their own ions and find out its potential? No, it is not possible, because the reason is there is always reduction associated with the oxidation, or oxidation is associated with the reduction. That means if you have reduction reaction, you will definitely have oxidation reaction. And if you have, say, oxidation reaction, you will definitely have reduction reaction. So all reactions are what? Redox in nature. So here, if you have a zinc, this is oxidation. So where is reduction? So you have to connect something that will give you reduction reaction. And if you have a copper, then it is reduction reaction. So you have to connect something that will show oxidation reaction, right? So generally we use some reference electrode. Here we use standard hydrogen electrode to find out the potential of the cell. The zinc is connected with the standard hydrogen electrode, whose potential is arbitrarily taken as 0, whose potential is taken as 0, and these cells are connected internally through salt bridge, externally through wires, and they pass through potentiometer. They pass through potentiometer, galvanometer, and we can find out potential of the cell. Now there is equation, simple equation, that the potential of the cell is given by equation cathode. Potential of the cell is straightforward, given by equation. Potential of the cell is equals to potential of the cathode minus potential of the anode. Remember, the cathode is an electrode where reduction takes place. Anode is an electrode where oxidation takes place. Now we know that anode generally carrying anode in case of electrochemicals, electrolytic cell is positive, and cathode is negative. But the basic definition is cathode is a electrode where reduction takes place. Anode is electrode where oxidation takes place. So here in case of zinc, it has negative charge. In case of copper, it has positive charge. So potential of the cell is found out by using potential of the zinc plus potential of the standard hydrogen electrode, and thus there is a determination of a potential of directly of zinc electrode, which is in contact with the zinc. That means you have to connect electrode with the standard hydrogen electrode, that is called as a reference electrode, or calomel electrode, which is also a reference electrode. By using calomel electrode or standard hydrogen electrode, we can find out potential of the cell. Then what is our topic? Our topic is Nernst theory of electrode potential in Nernst equation. Remember, to find potential of any electrode, you have to use electrode and couple with reference electrode, right? Then that will make a complete cell, and then potentiometer will give you reading. Then potentiometer will give you reading, and using that reading you can find out electrode of the potential of the electrode. Okay, that is the thing. But if you have this Nernst equation, what is that, and what is the use of that Nernst equation? See, if you know this Nernst equation, that is given by equation as electrode potential is equals to standard electrode potential minus RT divided by NF into natural log of concentration of metal divided by concentration of metal ions. You can write same equation as electrode potential is equals to standard electrode potential minus, you will keep the value of R in make temperature 25 degrees centigrade. F is a Faraday whose value is 96500. If you put the values of R as 8.314 joules per degree Kelvin per mole, and that of temperature is 298 Kelvin, and value of Faraday is 96500 coulombs. This equation is modified, and as well as the concentration of pure metal is taken as simply 1, then this Nernst equation is converted to electrode potential is equals to standard electrode potential minus 0.0591 divided by n into log of 1 upon concentration of metal ions. Or you can write this equation as electrode potential is equal to standard electrode potential plus 0.0591 upon n into log of concentration of metal ions. Remember, this natural log is converted to the log to the base 10. So this is Nernst equation. Okay, this is Nernst equation. What is the use of this? Now, if you know this, if you know the standard potential of the cells, if you know standard potential and temperature, you can find out electrode potential of any electrode. This is either reduction potential or oxidation potential. Generally, reduction potential is considered. So if you have standard electrode potential, standard electrode potential, standard reduction potential, and keep this standard reduction potential into this equation, you can find out electrode potential of any electrode using this equation, that is standard electrode potential plus 0.0591 into log of concentration of metal. And thus, there is no need of any potentiometer or any device to find out the potential of the cell. Okay, so that is the advantage of this. That is the use of this. Now you can modify this in terms of, say, for a concentration of zinc or concentration of silver. For example, let us modify this basic equation, that is E is equals to, that was proposed by Nernst, that is electrode potential is equals to standard electrode potential minus RT divided by NF into log of concentration of 1 upon M plus N. Remember here, N is valence. Instead of saying valency, we can also say that if metal pass into the solution and it form N plus ions and loses N electrons, so that N is this. This is oxidation. Or metal with charge plus N accept N electrons with the formation of metal. This is a reduction process. This N is this. Okay. So if the charge is plus 1, N is 1. If the charge is plus 2, N is 2, and so on. Right? So let us modify this equation in terms of zinc. What happens? Okay. So our equation is electrode potential is equals to standard electrode potential minus RT divided by NF into log of 1 upon M plus N. Let this M plus N be zinc. Now zinc reduction process is zinc plus 2 electrons with the formation of zinc. Then electrode potential is equals to standard electrode potential of the zinc minus R, it is 8.314 into T 298, N is 2, let keep it N as N, and F as 96500. Now convert this log to the base 10 by multiplying 2.303, then this becomes log of 1 upon concentration of plus N, or it is finally equals to electrode potential The total of this comes to be 0.0591 upon n into log of concentration of 1 upon, instead of writing m, we can write zinc plus 2, and this n is 2. So this is Nernst equation for zinc. Here, the electrode potential of zinc is equals to standard electrode potential of the zinc minus 0.0591 upon 2 into log of concentration of 1 upon concentration of zinc plus 2. So this was Nernst equation. Generally, this equation is used at 25 degree centigrade temperature, and that was in brief about Nernst equation. That's it. Now I hand over the session to sir. Yes, sir. So thus, in that way, the Nernst equation is useful in the determination of electrode potentials. Hello, sir. Am I audible? Okay. So in this way, I conclude this point about Nernst equation and Nernst theory of electrode potential. So if you have any issues or problems, you can ask. Whether anyone have any?
Sir, you finished?
Yes, yes, just.
Thank you so much, Pradhan sir. Really, it was very nice and wonderful session. The way you are explaining the electrochemistry, electrophysics, that in the while using diagrams and equations and other things. Really, it was very nice and informative and knowledgeable session that you have conducted today. We are appreciate your presence for this session, and thank you so much for accepting our invitation to be here as a resource person and delivering a very nice speech. I am very much thankful to the chairperson of this program, Dr. B.R. Bodke sir, for being with us, and I'm very much thankful to the vice principal of my college, Dr. V.G. Chavan sir, for being with us. My college librarian, Dr. Sadashiva Rote sir, is also with us. I'm very much thankful to him also. And once again, I'm very much thankful to all the respected dear participants those who are watching us on YouTube and those who have joined with us in this same Zoom meeting. I'm very much thankful to each and everyone. Once again, I'm very much thankful to the Honorable Resource Person, Dr. Patan sir. Thank you so much. Sir will be within a few days, he will be doctor. So that's why I'm calling him as a Dr. Patan sir. Thank you so much, sir, for being with us and giving your fruitful session. Thank you so much, sir. Thank you.
Thank you, sir, giving chance.